Hello everyone, it's Teacher Simon here taking you through AS Chemistry paper 9701 stroke 11 for May June 2025, and this is part 1 for questions 1 to 10. Question 1, we have iodine trichloride reacts with water in a redox reaction, and we are given the equation here. What are the numbers V, X, and Z in the correctly balanced equation? Now, what we are going to do here, since it is a redox reaction, we can try to use oxidation numbers to balance, okay? So I have iodine here, trichloride, then plus water, and then we are getting the HCl, then plus hydrogen iodide, then plus hydrogen iodate, and then we have hydrogen perchlorate. Okay, now let us look at the oxidation numbers here. For iodine, these two are all electronegative, but chlorine is much more electronegative compared to iodine. So that means it is the one that is going to take the negative charge. Okay, so it will have the oxidation state of -1, then iodine will have oxidation state of +1. For water, of course, hydrogen is +1, then oxygen is -2. Same here, hydrogen is +1, chlorine is -1. Then we go to iodine here. I mean hydrogen is +1, iodine is -1, +1. Then iodine, so if we have +1 here, 1, then plus the one of iodine is N, we don't know it, then plus oxygen, there are 3 of them. The oxidation state of oxygen is -2. Okay, then we equate to 0. So N here is going to be, first of all, this is -6 plus 1, you get -5. So when the -5 crosses the equal signs, you'll get a +5. So it will be +5 here. It is the same thing that is going to be here on chlorine, because they are in the same group, and you can see the compounds are looking the same. Okay, now after that, let's look at now iodine. So for iodine, I can see that moving from this one here, +1 to -1, there is the change is a -2. You see that? So 1 minus 2, you get this -1. The oxidation number change there is a -2, or I can just take it as a 2. Okay, but then there is also this one here, +5. So that means this one is a +4. You see, 1, then +4, then we get this. So this is a disproportionation reaction, because iodine here, we can see that it is reduced, and then here it is oxidized. Then let's go to chlorine. Chlorine from here to here, okay, we can see there is no change. But when you continue to, now, since this one there is no change, I'm going to leave it. Okay, I'm going to leave it. No, actually it is the change. Is the change there? No, this is -1, and then this is -1, so no change. Let me just look at take this one away a little bit. Let me just look at the change from here to here. You see that? So from -1 to +5, I think that is a +6. -1 plus 6, you get the what? The +5. Now, when we are balancing this equation, I'm going to get the change that is here, then I multiply it in the change that I get here. You just look at where the changes are. So if the change here is 2, then this one is 6. What is the LCM of the 2 and 6? It is going to be 6. So that means I can multiply this one by 3 to get the 6, not so? So that means the change I'm seeing here, I'm going to multiply here by 3, okay? And also this other side by what? By 3. Now, check what we are going to have here. Now, I'm going to have a 3 here, iodine trichloride, then plus, let me first leave the water here, then HCl, then plus, this is hydrogen iodide here. I'm supposed to put here 3, right? Then plus, now here there is a change also. So because there is a change here, this is a 4. Now the LCM of this and this is going to be 12, okay? That means this one I have to multiply it by 2, and you know. So, but let me first leave that one there. We have plus, I can just leave out that 3, then plus iodine, I mean hydrogen iodate, and then hydrogen perchlorate. Okay, now since here there is a 3, and when you look at our numbers here, there is 3 and 2. So suppose I put 3 here, then they're saying that now iodine this way is 3. That means when I come to this side, iodine also has to be 3. So suppose I put a 2 here, and here we are having a 1. Now the one that you are having here should be the one that is here, because like when I look at the options, maybe looking at this option here, oh no, when you come back to this one here, there is Z and also Z there, so the number is the same, you see. So if I put maybe a 2 here, that means even here we'll be having a 2, you see that. But let me first put the 2 here, then I leave a 1 here. Are we there? Then even here I'll be having a 1, but we usually don't write that 1. Then after that, let us try to balance others. Now chlorine here is 9. If chlorine is 9, now I'm going to balance these others actually using the numbers here. Okay. Oxygen, I can see these are 6 oxygens. So if there are 6 oxygens, I can put a 6 here. Do you see that? So when I put a 6 here, hydrogen now becomes 12. If hydrogen is 12 here, this one will be 1, 2, then plus the 2, you get 4. So we are remaining with 8 to make 12. Then I can put an 8 here. Now, this is our X, which is 8. You see? And I can see an 8. Then there is a 1 here. That is our Z. So actually Z is 1 everywhere. Okay? And then there is a 3 here for V. Okay? It is here. So let's see now if this equation is actually balanced. You can see that chlorine, we have 1 here, and then plus 8 becomes 9. Chlorine is 9. You see that? What else? Oxygen, we said it is 6, then 3 plus 3, that is 6. Hydrogens, 1, 2, then 3, 4, then 12. And also here it is what? 12. You see? So it is balanced when V is equal to 3, X is equal to 8, and Z is equal to 1. So I don't even need to continue with others. So I'll just leave my answer there as a C. Question 2. The rate of the reaction between a reactive metal and an excess of a dilute acid is investigated. The total volume of hydrogen gas produced is recorded every 30 seconds for 3 minutes. 3 times 60, then you get 180. So in 3 minutes, we have 180 seconds. So the first 30 seconds, we are seeing that the volume of hydrogen is what? Is 64. Then you continue the next, now it increases to that. So there's a change in here. That will be 36, then plus 5, that becomes like 41. Okay. Okay, so now what are they telling us to do here? The average rate of reaction during the first 30 seconds is P. Rate is equal to, we have to look at the volume. For this case, it is the volume of hydrogen, right? Volume of hydrogen, then divide by the time taken. Okay, so P is going to be equal to, the volume of hydrogen here is 64. So it is going to be 64 out of what? 30. Then they are saying the average rate of reaction during the 30 seconds, the last 30 seconds is Q. Now last 30 seconds from here to here, you're seeing they added 6, not so? So that means Q is going to be equal to, the volume there is 6, then divide by 30, which is the same as 0 2, 1/5. And then they are saying what is the value of P minus Q. Now P minus Q is going to be 64/30 minus 0 0.2. So let's see what we get here. 64 out of 30, then minus 0 0.2. That is 1.93 recurring, okay? 1.93333, like that, it is recurring. And our answer, when you look through here, it is going to be B, to 3 significant figures. Question 3. In the diagram, curve X was obtained by measuring the volume of oxygen produced during the decomposition of 100 cubic centimeters of 1 molar hydrogen peroxide. A catalyst of manganese 4 oxide was used. Which alteration to the original experimental conditions would produce curve Y? Now, when you look at curve Y here, we are seeing the yield has increased, okay? Since the yield has increased, that means you must be having more reactants. You get it? So the concentration of the reactant, hydrogen peroxide, must be increased, okay? If you don't increase the concentration of the reactants, when you put a catalyst, it is just going to increase the rate of a chemical reaction. You still, you get the reaction that is faster. So if this is, let's say, the curve, then when you put a catalyst, the rate of reaction increases, so it just bends to the right, but it is going to level off. It levels off first, okay, but then it will be on the same line. It will give you the same what? Yield. You see that? Then what else? We also have, they are talking about temperature. When you increase the temperature, you're also going to increase the rate of a chemical reaction. You see that? But not the yield. So the alteration we are going to have here, they are saying adding more manganese 4 oxide, that is a catalyst. It is not going to increase the yield, but rather the rate of the chemical reaction. Adding some 0.1 molar hydrogen peroxide. Now here we are adding some reactant, and I've told you that when you add a reactant, then you might receive what we call, you might receive more products, so the yield might increase. So that means even our answer is supposed to be C. When you add water, of course you are reducing the concentration of hydrogen peroxide. Raising the temperature, it will just increase the rate of the chemical reaction. You see? Then question number 4. The first 7 ionization energies of an element between lithium and neon in the periodic table are shown here. They are here, they are increasing. So every time you remove an electron, okay, there is a proton that is left in the nucleus without a counter electron, you see? So the nuclear attraction for the outermost electrons, or the electrons that are remaining, it is going to be stronger and stronger. So that's why whenever you are removing an electron successively, you are going to see that the values are increasing. What is the outer electronic configuration of the element? Now, outer electronic configuration of the element, and when we look at all of these ones, we see this is the second principal quantum number, okay? There is the first shell, and then the next shell is the nucleus for shell. So we are looking at this one here, okay? Now, that means this one is a period 2 element, okay? Now let's see. The jump here is very small, small here, 5,000 to 7,000, then 7 to 11,000, then 11 to 13,000. Now you move from 13 and you go to 71. So this is a very large jump. So because of this very large jump, that means these first 6 electrons are removed from the same shell, but this one is removed from this other electron, the seventh one, is removed from the inner shell. That means this element has 6 electrons in the outermost shell. And if it has 6 electrons in the outermost shell, then we have 2 electrons in the s, and then in the s orbital, and then 4 electrons in the p orbital. So the answer becomes C here. Question 5. The reaction of hydrogen with oxygen is shown. This is the one here. And they are saying which expression corresponds to the standard enthalpy change of this reaction. When you look at hydrogen here, it is an element in its standard state. Okay, even oxygen, an element in its standard state. They appear as diatomic what? Molecules. And then here we are getting water as a liquid. That is its standard state. Okay, and then we are getting 2 moles here. If it is enthalpy of formation of water, we are looking at 1 mole of a compound that is formed from its elements in their standard states. But here we are forming 2 moles. You see that? So that means when you look at our options here, now they are saying 2 times the standard enthalpy change of formation of water. And it is true, because for standard enthalpy change of water, the standard enthalpy change of formation, it is going to be when you are forming 1 mole. But this is 2, that means you will multiply this by 2. And the answer has to be A. And even here it is enthalpy change of combustion of hydrogen. If you are combusting hydrogen, then it has to be 1 mole. But these are 2 moles. You see that? 1 mole of a compound that is completely burnt in oxygen. That is what we call standard enthalpy change of combustion. Question 6. P is a compound that burns in an excess of oxygen to give carbon dioxide and water only. 2.20 grams of P contains 1.20 grams of carbon and 0.2 grams of hydrogen. When P is added to a solution of sodium carbonate, bubbles of gas are seen. What is P? Now, when you look at this 1.2 and you add 0.2, you will get 1.4. Okay? Now that means there is something left here. So that would be for oxygen. That means this element here must be having carbon, hydrogen, and oxygen. And even what we are seeing here, there is carbon, hydrogen, and what? Oxygen. Now let us look for the mass of oxygen. It will be 2.20 minus 1.2. When you add 0.2, this is 1.4. And then 2.2 minus 1.4, you get 0.8. So the mass of oxygen will be 0.8, this of hydrogen is 0.2, then this of carbon is 1.20. So I'll find the moles. To find the moles, it's like I'm finding the empirical formula, okay? Then I'll divide by 12. This one will actually give us 0.1. Then when I divide this one by 1, because the AR of hydrogen is 1, then we shall get 0.2 here. And then we shall divide this one by 16. This one will give us 0.05. Then we get the mole ratio. We divide all through by the smallest value. So 0.1 we shall divide by 0.05. Then 0.2 divide by 0.05. And then also this is 0.05. We divide by 0.05. Of course, this will be a 1. This will be 4. Because 5 goes into 20 4 times, and then 5 goes into 10 2 times. So that means the empirical formula is going to be C2H4 or. You see that? C2H4 or. Remember, the empirical formula can be the same as molecular formula. You see that? Now, when we look at this one here, if the empirical formula is the same as the molecular formula, this one can be maybe CH3, CHO. Can it be HO? Like that. That can be the one. Okay? Because the 2 carbons, then 4 hydrogens, and then an oxygen. You see that? Now, they said when P is added to a solution of sodium carbonate, if this is the P and you add it to sodium carbonate, they are saying bubbles of a gas are seen. Now, if bubbles of a gas are seen, this is an aldehyde. It does not react with sodium carbonate. So that means the answer cannot be this one here. Okay, it can't be that one there, and it cannot be this C here. Alcohols do not react with sodium carbonate, so we have to look at this one here and this one here, the carboxylic acid. Now for us to get the carboxylic acid or any other, now this is the empirical formula. Suppose I get this one here and maybe I multiply it by 2. So when I get this one here and I multiply it by 2, now also here, this one will be off. It's a carboxylic acid. It will be off. It has 2 carbons. You see that? But here we are seeing, for the empirical formula, we are seeing 1 oxygen here. So there is no way you can get this one as a carboxylic acid. Now, when I multiply this one by 2, the carbons are going to increase. So I will have C4, then H8, and then O2. You see that? So this one now gets off. You see? Because for each it has what? 2 carbons and 2 oxygens. So when I multiply, because this is the empirical formula, that means to get any other molecule, I'm going to multiply here by by a whole number. When I multiply by a whole number, then we cannot have 2 carbons. They are going to be more than that. They are going to move in multiples of 2. So when I multiply by 2, then it will be 4. When I multiply by 3, it will be 6. Now checking this one here, it can be CH3, CH2, CH2, COOH. Okay, there are 4 carbons, but how many hydrogens? 5, then 7, 8, and then 2. So it's this one here. And you can see that this one here is actually this. So that means our answer is going to be D. Question 7. Substance W has the physical properties shown. They are saying that the melting point is high, the boiling point is high, then electrical conductivity of the solid, it is very poor. Okay, the electrical conductivity of the liquid, it is good. That means this one is an ionic compound. It has to be an ionic compound, because ionic compounds, they conduct electricity when they are in aqueous state or molten state. Okay, so in aqueous state, that means you dissolve them in water. Okay, and then the ions are separated and then they are free to move. Then in the liquid state, that means you have melted them, and again the ions are free to move. But in the solid state, the ions are in a lattice, they are compacted. Okay, so they cannot move. That's why they cannot conduct electricity. So we have to look at ionic compound. Okay, silicon dioxide here, this one is what? Covalent. This one is a covalent compound. Okay, then sodium fluoride is ionic. Yes. Iron, this one is metallic. Okay, we are looking for ionic what? Compound. Then this one is ionic. So B has to be off. Also the C has to be off. Then they are saying in water, sodium in water, this one is going to dissolve, sodium fluoride in water. So when you say plus aqueous here, you are going to get sodium ions, then plus what? The fluoride ions. You see that? Now these ions are free to move. So this one will be actually conducting electricity in water. So this one will also be off. That means our answer is what? Is A. Actually, aluminium oxide is insoluble in water. Aluminium oxide does not dissolve in water, neither does it react with it. So that's why we have these overhead power cables, okay, of electricity. So aluminium first reacts with the oxygen, then it forms that layer, and then it covers it. Okay, and then because this layer cannot react with the oxygen, then it acts as a protective layer. So that's why our answer is what? Is A. Question 8. Which diagram represents the lattice structure of sodium chloride? Now the lattice structure of sodium chloride, we have sodium, they are positive ions. Okay, then chlorine, they are negative ions. Actually, sodium ions are surrounded by 6 chloride ions. So there is one here, there is one here, there is one here, there is one here, then there is one on top here, and then one going the other side. Okay, like one facing you here, it's just like a pyramid. Let me just show you something small here. If I may have the sodium here, so there is a chlorine here, there's a chlorine here, there's a chlorine here, there's a chlorine here, chloride ions, then there is one down there, and there is another one there. So there is that network there. Okay, we have that by pyramidal structure, something like that, but we can put it in a cuboid. This one will take me time to draw it, but we have something like this. So this is actually how the structure looks like. Now I'm going to use these colors. If red is for sodium, okay, here, then chlorine has to be here. Let me put it in green. Chlorine here. Okay, then we shall also have here chlorine, then also chlorine here, and chlorine here. You see that? So how many are around this oxygen? I mean this sodium. You can see there is this one here, 1, then all of them are connected to the sodium, 2, then 3, then 4, then 5, and 6. You see, that is how it is, and they continue. So if here I'm having green, then here I should have red, green, red, then red. You see that? Then now we have here green, then green. This has to be green, then green, green here. You see? Then that means here we'll have again green here. Now red here. You see? Red here. Okay, then we must have a green here. Okay, and what else? There has to be a red here, and then also a red here. So if I take this one to be for sodium, then the green one, the green for chlorine. So that is the cuboidal structure of sodium chloride. 6 of them, but I've just picked, because this one is continuous, but I've just picked the one that is in the middle. Okay, the one in the middle here, surrounded by 1, 2, 3, 4, 5, and then 6. Okay, that is like that. Now sodium as an ion, by the way, when we look at the structures, sodium has remember, it is 1s2, 2s2, 2p6, 3s1. Then chlorine, 1s2, 2s2, 2p6, then 3s2, 3p6, 3p6 will be 3p5. Okay, so this one here is bigger, is a bigger ion. Okay, because there is one more shell on it. Okay, yes, it has a higher nuclear charge because it has more protons, but the nuclear attraction is smaller. Okay, nuclear attraction is smaller because of the increased shielding here. Okay, so we expect the ion of chlorine to be bigger in size. So our answer is going to be, and here this one is off because they are using just sodium as an atom. It is a lattice structure, it has to be ions. Okay, so this one has to be off, you see, and how this one is drawn, it is actually for the metallic structure. This is metallic bonding, okay? Metallic structure, where we have a C, this lattice of positive ions surrounded by a sea of delocalized what? Electrons. So even this one will be off. Now, like I've told you, sodium, which is positively charged, it has a smaller ionic radius. So we should look for sodium when it is small, but here it is big. So this one has to be off. And our answer here has to be a B. So B here. You can see here they are putting 1. Even the chloride ion has 6 sodium atoms around it. Okay, so you'll have 1 here. This is 2. This is 3. This is 4. There is 1 that is facing us here, and then there is 1 that is behind there. It is octahedral. Okay, but those ones, this is a 2D, so we cannot see it, but in this 3D you can easily see. You see that? Question 9. An aqueous solution X contains substance HQ which behaves as a weak acid, and it dissociates partially into these ions. Okay, then they are saying the soluble salt sodium here with the Q is added to X. What happens to the hydrogen ion concentration and the pH in X? Now when I put this one here, the sodium of the salt here of sodium, it is going to dissolve completely. Okay, so it is going to split into its ions here. This will be aqueous, and then this one here also Q minus aqueous. Now this one is an equilibrium reaction, and we have introduced many more ions of Q. So that means the concentration of the Q ions here has increased. Okay, so this will disturb the equilibrium. So using Le Chatelier's principle, the position of equilibrium is going to shift to the left. You see that? Because Le Chatelier's principle states that if there is an alteration in the factors that affect a dynamic equilibrium, then the position of equilibrium shifts to the side that opposes or that minimizes the change. So in this case, the position of equilibrium will shift to the left. So these Q ions are going to react with the hydrogen ions to form this ionized solution. This ionized acid. So meaning the concentration of hydrogen ions is going to reduce. So that means I will look for decrease. Are we there? But then the pH, when the concentration of hydrogen ions decreases from the solution, then that means we are going to have a higher pH. The more the hydrogen ions you have in solution, the lower the pH, because the solution is acidic. You see that? So that means the pH has to increase, and therefore our answer has to be B. Question 10. Dinitrogen tetraoxide decomposes reversibly. This is what we are having here. It is an endothermic reaction. An equilibrium mixture of dinitrogen tetraoxide and nitrogen dioxide gases is placed in a closed container under standard conditions. Case C is this one here. Then they are saying that the conditions are changed. Okay, conditions are changed. Now we are looking at again Le Chatelier's principle. Under the new conditions, Kc is now this. Now Kc has increased. Are we there? The only change that leads to the change in the Kc, the equilibrium constant, is the change in temperature. Are we there? But when you increase, like let's say this is 1 mole, these are 2 moles, we know that pressure is inversely proportional to volume. Okay, so pressure is going to increase if you reduce the volume, but volume also, we know that it is directly proportional to the number of moles. Okay, now the number of moles are many this side, so that means volume has increased. That means pressure has to reduce. Now you have to decrease the pressure. Are we there? When you decrease the pressure, the position of equilibrium is going to shift to the side now with more moles. Okay, because V is directly proportional to what? To N. So it will shift to the right. You see that? When it shifts to the right, it will do so until equilibrium is established. And when equilibrium is established, you will get back your Kc that you have here. You see that? Then that means we are supposed to look at this option here. But since Kc changed to this one here, then it is increasing what? In temperature. Because this one empowers the molecules to move faster, and then you are going to have more frequent what? Successive collisions. And in their case is going to change. Okay? Because many have been empowered to react, and when they react, they give you the product. In that case, then that means you're going to have more of the products, very many products, and then the Kc. Remember, Kc is supposed to be the concentration of the products. We have this one here, raise it to that power, the number of moles in the stoichiometric equation, then divide by the concentration of the nitrogen tetraoxide. You see that? So we're having more of this when we increase the temperature and very few of these. Kc has to increase, as simple as that. So that's why our answer is C.